up to this point, we have seen many things. One of them is why you have different kinds of radiation. In fact, last Tuesday we talked about that. You should now have a very good understanding of why, of all the things that the nucleus can do when it falls apart, it does an alpha particle. That's because of the magic numbers. It does a beta particle. Why is that?
To get CNN equal.
Yes, to get CNN equal. That is the most basic reason for it to happen. And gamma?
For the transition states.
Between the nuclear shells, exactly. So we know exactly why each of these things happen. So that's good. We know the processes that let them happen. And mind you, we just started out with quantum mechanics, yes? First lecture, basic quantum mechanics, we got everything from that, so that's nice. What we haven't spent much time on is how fast it typically happens. And for each of these three types of radiation, you have to get an idea of how to do that. They all come with a different way of calculating them. And one way I described last Tuesday was using the Fermi-Golden rule. And Fermi-Golden rule, as you might recall, tells you something. Well, if you have this situation that a piece of physics starts out in an energy state, then something comes along and tries to perturb it, tries to push out that energy state, goes to another energy state. How often per second do we expect that to happen? That's what the Fermi-Golden rule tells you. The exercises that I would like to discuss with you on Tuesday, I sent them to you yesterday, are actually on that you actually go through that calculation for beta decay. And you actually get numbers out. And they fit with the experiments, so that's nice. Again, just quantum mechanics, do the math, you get actual numbers, and they work. Now, for alpha, the situation is very different. You cannot use the Fermi-Golden rule very well, so what you have to do, and this is just an outline, the full details are in the video that I posted on YouTube, but here's the idea. Since I posted it, there have been 5 views. Was that you?
I saw it.
You saw it, yeah. You don't have to say that to do me a favor though.
No, I actually did.
Okay. So you know how that works?
Yeah, I have the graph and everything.
Oh,
but
really?
you go ahead.
Okay.
Do your thing.
Yeah, well,
no, I could never.
Okay. There we go. Here's the idea. It's a sort of a semi-classical, semi-quantum mechanical approach. Here's the classical part. We're going to assume that the nucleus actually consists of protons and neutrons. This, by the way, is already somewhat classical, because the idea that the nucleus is just really these little billiard balls sticking together is not very quantum mechanical. But sure, let's assume that that's the case, and we're going to assume that somewhere in there is this 4 billiard balls stuck together that is called an alpha particle, 2 protons, 2 neutrons. And again, you know why the nuclear shell model, magic numbers and such. Now, of course, this by itself, is very classical. Yes, the idea that the nucleus consists of billiard balls, and there's already an alpha particle in there, just waiting for it to go out. That's not how it happens. In real life, you have just these particles just floating around, and when they go out, they sort of decide to become an alpha particle. It's not like the thing is already in there or something, but we're going to assume that, just to get a good approximation of how these things work. Now, the idea is, this thing is floating around, bouncing from one side to the other. This again is very classical. Why? Why is this classical? Why is this quantum mechanically not correct? The idea that there's this alpha particle, okay, sure, that's one. And the second one is that it just floats around, bouncing against sides.
That Heisenberg's uncertainty principle, that we cannot state the direction with the same.
Exactly. Well, there's 2 points actually. One of them is Heisenberg. That you cannot precisely say, well, it's going with this velocity at this moment, right? So that by itself is wrong. We actually derived the Heisenberg uncertainty principle, so you know that the idea, well, the thing floats around with the velocity v is just wrong, just from the outset. It's very classical. And the second thing is, you don't know in which direction that is traveling, because quantum mechanics tells you only probabilities. It might be flying in that direction at this moment, might also be flying in the other direction. It might be here at this moment, might be there at this moment. So the whole idea that it follows this full trajectory with a well-determined velocity is extremely classical. But anyway, that's what we're going to do. Now, here's the idea. Let's suppose that we know the radius of the nucleus, big nucleus. we're going to calculate how often per unit time per second you expect this alpha particle to hit one of the boundaries. That by itself is a classical calculation. Because what is the maximum distance that the thing can travel from one side to the other? It's a spherical nucleus, radius is r, 2r. Okay, so the maximum distance, again extremely classical this part, that it can travel, that's called delta x, is 2 times r, 2 times the radius of the nucleus. So there's that. Now suppose that you also know with what velocity the particle is flying around. Again, extremely classical, but let's suppose that we know this number. Interesting, where do we get the number from? This classical velocity. I have to put in a number at some point. I have to tell you with what velocity, it's called V alpha, velocity of the alpha particle. Typically, where would I get this from? It's not like I can just, stick an or just stick a thermometer in there in the nucleus and it says, well, the velocity happens to be this and that or so.
Yeah.
Well, let's say that this alpha particle in there has an energy E alpha. Would that help? Connection between velocities and energies? Newtonian mechanics.
Yeah. Half mv squared.
Half mv squared. There you go. So suppose that we know the energy with which a particle flies around, and yes, we can calculate that in a very easy way that I'll show you later. But if you know this one, and of course you already know what the mass is, you can calculate the velocity. So let's put that in. It will give you 2, if memory serves, 2e alpha m, I think. There you go. Now, where this number comes from, I'll tell you later. Maybe you already know, by the way, if you think about it for a little bit. So what we now have is how far it can maximally travel and with what velocity it typically does so. And that gives you a measure of how much time it will take for the thing to go from here to here. Because as you know, if things travel with constant velocity, no, that's wrong. Then you know that this formula holds. In other words, that you know that the amount of time that it takes the alpha particle to go from here all the way to over there is just delta x divided by its velocity, and delta x is 2r, and its velocity is 2e alpha divided by its mass square root. So we now know, again, very classical, but we now know how many seconds it takes for the thing to move from one side to the other. But that also gives us an idea of how often it will hit the boundary of the nucleus. Right? I mean, if it takes this many seconds to go from one boundary to the other boundary, then the frequency with which it hits boundaries is 1 over that number. There you go. That's an important number for our alpha calculation in a moment. It's the frequency with which you expect the alpha particle to hit the boundary of the nucleus. Now we have to put 2 numbers in there. The mass of the alpha particle is always the same number. We have to get the energy from somewhere, and we have to get the radius of the nucleus from somewhere. We'll get to that in a moment, how we get to those numbers. But let's suppose that we know how to calculate this number, we actually get a number out of 5, or something like that. Here's the next step. If you want to know how often this alpha particle gets outside of the nucleus, you need 2 ingredients. One of them is, if it's here at the boundary, what is the probability for it to go out? Times how often it's actually at the boundary. It won't go out if it's over here, somewhere in the middle. It has to first travel to the side, and when it's at the side, then it travels out. So the amount of times per second that you expect the alpha particle to come flying out of the nucleus is a combination of 2 factors. Here's factor 1. The amount of times per second that hits the boundary. There you go. Times when it hits the boundary, what is the probability that quantum mechanics lets it fly out? So that's all we're going to need. The amount of times a particle comes flying out per second is the amount of times it hits the boundary multiplied by the probability of it flying out when it hits the boundary. This number we know. This we got from classical means. That's this expression. This is where quantum mechanics comes in. I find myself almost fully deriving the whole thing. So let's stop with the technical details because YouTube and such. But let me just tell you what the steps are. If you take here the potential energy that the alpha particle feels, it consists of two parts. For one thing, there's a potential well. That's the strong nuclear force that we modeled in our calculated nuclear shells. It's not a very good approximation because you know it sort of tails off like that, right? But it sort of looks like this. It's a potential well. This is what the nuclear force does for you. Let's call this R0 or something like that. Here's R. So this is the energy, the potential energy that the alpha particle feels because of all the other particles in the nucleus. Now what is then this R? It's the distance between the center of all these other particles and the alpha particle. That's that distance. Now of course you know that it is only the strong nuclear force. This is a good approximation. Gives you the first couple of matching numbers, but there's another contribution as well. Tell me. Well, you know, not necessarily somebody tell me.
The Coulomb repulsion.
The Coulomb propulsion. The Coulomb propulsion between two charged particles looks like this. Because you might remember what the formula is from just for classical electrodynamics. The Coulomb propulsion is given by this expression right here with an R, not R squared. R squared is for the force. And Q is the charges of the two particles trying to push each other out. And the approximation that we're going to make now is that at this part, all the way up to R0, it's a strong nuclear force that dominates. So we're going to forget about this part over here. And outside of R0, the Coulomb takes over. So this is going to be our new potential energy. That's the idea. Now suppose that we have this alpha particle. Here's its energies over here. And we're going to take its energy to be this number here. E alpha. It's the same E alpha that we have over here. Right. If this were classical physics, the particle would not be able to get out. Would not be able to get all the way over here to big R. Why? Because it doesn't have enough energy to jump over the barrier. Classical physics, Newtonian physics tells you this is impossible. But not so in quantum mechanics. Quantum mechanics has a tunnel effect. I know you've had this, right, in your quantum mechanics course. Tunnel effect. But even if you don't have enough energy, you do get particles at the other side of barriers. But it depends on two numbers. It depends on how wide the barrier is. So for this particle with this energy, the width would be this number A. And it depends on the height of the barrier. That's called V0. And I'm going to borrow an expression from quantum mechanics what the probability of tunneling is, the probability of it flying out. The exercises that I sent you, let you calculate this. And it guides you through it in a number of 5 or 6 steps or so to get to this expression. I forgot what's in the numerator.
It's 16.
Thank you. I was
Exactly.
and the squares of the
Yeah.
twos. Yes.
Yeah.
Thank you. There you go. It's this expression. There's a couple of other numbers in there. There's abbreviations K and kappa. Again, getting this result is one of the exercises for homework that we're going to discuss on Tuesday. Kappa, K, excuse me, is given by this number. So this is a measure of the energy of the particle. And kappa is almost the same expression. H bar squared alpha V0 minus V alpha. There you go. So there's that. Again, go through the exercise, guides you to this result in a number of steps. This is the result.
Is that small k and big K?
Yes, this I call small k, and well, my handwriting doesn't very much allow it, but it's a Greek letter. I tried to make a kappa out of that.
So is it H bar or small k?
This is an H bar. Yes. And again, this k here tells something about the energy with which the alpha particle came flying. That's just, you know, up to some numerical factors, it's just a measure of the energy. And this big K, kappa, is a measure of this energy difference.
Mm-hmm.
The difference between how high the barrier is and how much energy it has. In other words, it's a measure of how much the alpha particle is lacking to jump over the barrier. That's what this thing tells you. You plug this in, you get a number out. Here's something interesting from a physics point of view. Can you see here that can you check if this is K or kappa?
I have it as kappa, I think.
Yeah, it's
I don't, yeah. I can't even read my own handwriting.
Okay, well, just from a physics point of view, I knew I made a mistake, because what you see here is that if the energy difference, this difference between energy, the lacking of the energy of the alpha particle is too big, the less energy it has compared to the barrier, the bigger this number gets, kappa, and the smaller the exponent gets. In other words, it becomes exponentially more difficult for the particle to come flying out if it lacks energy. That's what it says. So I knew I made a mistake here, because the K would say, oh, you know, if you have more energy, it becomes more difficult to come flying out. Well, that doesn't sound physically right, so I could correct myself there. So, okay, so there's that. You can see that how the more the alpha particle lacks energy, the more difficult it gets for the thing to come flying out. That's what it says. There's another thing going on, and that is that if the width, where's the width? Here's the width. If the width is very wide, the same thing happens, and this thing also becomes very big.
Yeah.
Which also makes sense. The wider the barrier is, the more difficult it is for the thing to come flying out. So everything that you want to know is in there. Now that's good, because this number, the probability of this particle to come flying out of the barrier is exactly that number. Right? We need the probability that quantum mechanics lets an alpha particle cross the boundary. Well, that's what the quantum mechanics tells you. That's this. So we have all that we need. This one is over there. This one is over there. And we can calculate how often particles you expect to come flying out per second. In other words, it's decay rate.
Yeah.
Do the measurement, compare to experiment, see that it works.
Yes, sir.
Yes?
What is the small kappa mean again?
The small k is just another measure of its energy, the energy of the particle. Yeah.
Mm-hmm.
Small kappa.
Well, there's no small kappa, there's
only
there's curly k and there's another k. Yeah.
Sorry, Thomas.
you're talking about the H bar. Right?
No, I was talking about the kappa.
Yes, well this is an actual H bar, yes.
Decay. Decay.
Yeah, right. Again, in my own calculation, H bars are all 1, so I never care about these things. But yeah, sure, this is an H bar squared. There you go. There's a lot of comments that can be made right now. Now, you might have seen from the email that I sent all of you yesterday or the day before that, is that I need another dynamic duo to do exactly this calculation for an alpha particle of their own choice. So actually go through this calculation. Volunteers.
When would the presentation be? Monday?
Tuesday.
Tuesday, oh sorry.
I'd like to make a case for those taking quantum mechanics because we have a midterm on Monday and we're going to be spending the whole weekend studying for it. So we want.
Oh, but you come across this one too, then, right?
It would be good practice for the
When midterms on Monday? No, I mean, that's possible. No.
But your point is that the timing is not perfect.
Sorry?
Your point is that the timing is not perfect.
Yeah.
I can do it, I'm not taking quantum.
Okay. You know, if it doesn't interfere with your other plans, say because you've already done quantum, so you don't have that issue. If somebody else would like to go, because we are on a schedule in the sense that we only so many tutorials, and everybody needs to go at some point. So your problem is solved. He never had a problem to begin with. Anyone? Yeah. Okay. Good. Thank you. Let me make some comments to help you along. Just as I gave the previous group gave the hint as well. There's something wrong with this expression. Well, this expression is correct, given that the barrier is rectangular. Because I start out with its height v0, and if you do the quantum mechanical calculation, again, refer to homework exercise, then this only holds the moment that it sticks to that, but of course it doesn't, it goes down. So you have to find a way to compensate for that, the fact that it goes down. That's
So
all.
after R0, okay.
But if there's anyone who wants to give these two gentlemen a hint, yes.
So two questions. One, that will we consider tunneling effects in this?
Yes.
And two, is that an exponential fall of them?
Yes. Here's the exponential, and this whole expression is the tunnel effect.
Oh, okay.
So how to compensate for the fact that this expression officially only holds for a barrier that is friendly enough to actually stay at this height instead of going down itself? This will be a gross overestimation, yes? Because it becomes more easy for the thing to tunnel, so this probability is probably way too low. It's too low, it's an underestimation then. So how to compensate? Well, that's actually part of the exercise. Maybe somebody wanted to drop a hint.
Adding in the epsilons, I don't know.
What do you mean?
I mean, if it's falling off too fast, if you add in the epsilon which goes to infinite, I don't know. Something
Oh,
similar.
I see. Oh, that's a clever trick. Okay. So you actually artificially put in an exponential.
Yeah, we just called it like last time that we did epsilon, we see the three
Yes.
or 4 different stages in R.
Yes.
And then I decide where this exponential will drop off.
That will be a trick.
Zero.
Yeah, that will be a good trick. Another trick is to actually go back to the Schrödinger equation, because this symbol comes from the Schrödinger equation, and instead of putting in a rectangular one, actually put in the Coulomb one, and see if you can solve that, either numerically or maybe by analytical means. I wish you good luck. It can be done, don't worry. So the assignment, as you can see in your email, is do the calculation, take any nucleus that sends out alpha radiation, so you know what numbers to plug in. Do the whole calculation, see what number comes out, see if it lines up with the experiment. If not, that's fine, but try at least to see why it doesn't. So that's the idea. One more comment. Where do I get this number from? R. The size of the nucleus, what the size of the nucleus is. Where do we get that from? Where do we get this from, by the way? The width. Yeah, it's called A, but where do I get it from? Where do I get the height of the barrier from? It's on the board, by the way.
Yeah. It's the K and the A. in the exponential factor of fast algebra.
Well, yes, but how do you get the number?
Oh, that's this, the A would be the distance of closest approach. It's the Coulomb potential, right?
Yes.
So A would just be the distance of closest approach. You could solve for that very simply.
Okay, but how would you do that? You're right.
You take the Coulomb potential and set it equal to
Okay,
the
that's it. Yep.
law.
All right.
That's enough.
No, it's fine, thank you. No, it's a good comment. No, you're right, of course. I mean, if you want to know this with one thing that you know at this point, by definition of this point, this line crosses that line. In other words, this one is equal to that one. And you can solve for r, you get this number. This number. If you also know this number, then you know the width. And such and follows. This is what you meant in this, yes? Right. Anyway, I will leave that for now. This is the physics. The rest is just doing the math. Let me just say that if you do the calculation, you have to be ridiculously careful that the numbers that you put in are highly significant. It's because this exponential goes down like something that goes down very fast. It goes down extremely fast. So you very easily miss a couple of orders of magnitude. If you miss one of these numbers by the 5th decimal point or so, you may find that your actual outcome is 3 times bigger or smaller than you would expect. So be ridiculously careful with the amount of decimals that you put in. So there's that. It also accounts for the fact that decaying particles, nuclei that fall apart using alpha radiation, have such a huge range in its decay time. Some of them take seconds, milliseconds, and some of them take millions of years. That's again because of this. This thing that makes it's the exponential that makes all the difference. Okay, there's that. So good luck to you both. We'll see on Tuesday how things go. Questions? Tuesday is going to be an interesting day because that is the day we're going to see how we can calculate the numbers for alpha radiation. And if you've done the homework that we're going to discuss on Tuesday, you're also going to see how to do it for beta radiation. And then we have made the full connection from postulates of quantum mechanics all the way to experimental physics, and we can all rejoice and be happy now. So that's nice. Interesting day, full circle. Okay, if no questions.
Can I ask just one question?
Yes.
I'm sorry, I think it's my fault, but why does the energy drop off to 0 once it crosses the Coulomb barrier?
Why the energy doesn't drop off to 0? It doesn't.
The potential energy.
Oh, the potential one. That's because of Coulomb interaction. It becomes smaller at big distances. And at that point.
No, but the other side, when R is less than R naught.
Oh, it gives, of course, it gives a contribution. But we're going to assume that the potential welliness of the strong nuclear force is much stronger. That this going down, some negative number, fully compensates for the fact that this one wants to go up. It's an approximation.
Because I was thinking that there would be potential greater than 0 because of the strong nuclear force.
Yeah, but that would lower the potential energy. It would try to keep the thing in.
Oh, that's true.
So this thing is just some steep well. It's very low, and it's much lower than this thing wants to go up. Of course, not at R0, because of infinity and such. But in theoretical physics, we try not to worry too much about infinities. Okay, so there's that. Let's now go to the semi-empirical mass formula, because we still had a couple of exercises to do with this. Now, somebody like to write down the semi-empirical mass formula? It's called interactive teaching and such. I give the marker to somebody. No volunteers. In that case, we'll let fate decide. That's what I did with my high school students. If nobody volunteered, I took out a coin. And I flipped it a number of times, all the way until somebody got to the point that they had to write something. Just ask for the semi-empirical mass formula. Let's see. Oh, there's only 3 women, lots of males. I wanted to make the division between males, females, 50%. Doesn't work. How about blonde versus dark haired? Does that work? You're a special case. I'll take you as blonde, okay? Blonde-ish. You're Eric blonde-ish? Yeah, no, that's, we'll call it blonde. Okay, let's call it group 1, that's you and the 3 of you, and then there's group 2. I heads and tails, I don't have a coin with me, but I actually have a card with a head on there, that's mine. So let's flip the thing a couple of times. If it's heads, the blonde people are still in the running to make it to the first steps. Alright? It's heads.
No.
Yes, we're in the blonde group. Fortunately, the Semi-Empirical Mass Formula is in your book, so you can easily just... But I might ask you some questions when you're there. I'm looking at you as if you're going to be the person, but we'll see, because now we have two females, 2 males, so females are heads, males are
the other part.
The other part, the tails. There we go. Males. Ryan, any preference? It also doesn't matter much for the outcome, yes? The probability is still going to be 50%. Yeah, you should actually talk to people who think, well, it landed on heads 2 times, so the next time it's going to be tails, because I think keep track or something like that. But okay, let's say heads, tails. There we go. But do you mind? Do you mind?
No, as long as it's one is the correct one.
What do you see? Going to do some fun stuff with the Semi-Empirical Mass Formula. Thank you. I don't know, one of them works, the other one doesn't work, let's have to see. It's very important that you know this formula. Thank you. Very important that you know this formula, and especially what the physics is. While he's writing, I hope that everybody remembers what each term stands for. It's not completely a new thing that's on the board right now.
We'll write down this.
We're going to need it later on, so if you wouldn't mind, yes please. You might remember that this last term is writing down, this delta, says something about whether the amount of protons and neutrons are even or odd. And that makes sense. That's something to do with the spins. Spin alignment. Yes. Where do you get the power a minus 1/2 from?
I think I read that in the book somewhere.
Okay. Zero. Now this should make sense to you. Why there is a difference between even number of protons, even number of neutrons, and permutation of that. Why that gives you different binding energies. Why it's exactly this particular mathematical form is just a matter of fitting. This is people writing it down. Thank you.
Is that A minus 2Z or A minus RZ?
2.
Oh, okay.
Yes. This thing accounting for the fact that protons and neutrons try to get to the same number as much as possible. And in fact, we talked about that last week. We did a very quick exercise in which we took some isotope and said, well, it doesn't have the same number of protons and neutrons. So what kind of particle will it send out to make that happen? And some isotope came out, but the isotope wasn't the most stable of isotopes. And I think that you asked the question then, oh, but lead is a very, very good counterexample, right? It has many more neutrons than it has protons. So I thought it was a very good question. So I thought, does it have anything to do with the Semi-Empirical Mass Formula not being accurate enough? Or are we just misinterpreting something? So I took a little moment of time on the train again to work that out. And I would like to show you what the answer is. So again, what the question is how much do nuclei try to get the amount of protons and neutrons the same? This term says that it does try to, but of course these other terms also make contributions. So what I did was the following, and it will lead into the exercises. What I did was the following. I said, you know what? Let me just take the derivative Z. Let's take the derivative of the semi-empirical mass formula with respect to Z and set it to 0. And as you know, that will give us the value for Z for which the E is either maximal or minimal. And it turns out we're going to look for the maximal part because, as you know, the more energy the nuclei have, the stronger they keep together, the more stable the thing is. It's not that difficult because you can already see what comes out, yes? Doesn't depend on, oh, let me make a comment here. I'm going to say that A is a constant. Is that an issue, by the way, because A depends on Z itself, yes? Because A is just a sum of N and Z. So am I allowed to say, well, go to derivative with respect to Z, but keep A constant?
Partial derivative.
But I would call, yeah, that's a mathematical answer to the question, but what does it physically mean? I mean, A is just Z plus N. I'm going to keep A constant. Whereas the derivative by definition means I'm going to shift Z around a little bit.
Yeah.
Is there an issue?
Not for large A.
How does that make a difference?
Because the changes are of the order epsilon, but if A is small, then epsilon.
Oh, I see. Oh, I see what you. Oh, yeah. That's actually yeah. I think that's a good comment. Yes. Here's another way of answering this question. By definition, the derivative means I shift Z around, and I shift it so much around that I find a Z that makes the whole thing goes into 0. How can I do that? Shift Z around and keep A constant? Well, by shifting N around the other direction, yes? So I'm fully free to make this statement. So I'm going to do that. Take the derivative of this one, and A is a constant. Gives us 0. Derivative of this one, with respect to Z, A is a constant, gives you 0. This one, here's where life becomes a little bit more difficult, but not really. Derivative of this one, if my math is okay, it's something like this. Z squared, yes, that's correct. This one, I don't know why I write down 4. A, what's that? That's 4 to the 8Z squared minus 2A. Feel free to correct me because I'm doing this real time. I think this is correct. Okay. If I multiply this out with 4Z squared, the derivative of that will be 8Z, not squared. There you go, first mistake. And secondly, I would have an A squared, no derivative, I would have minus 4 times AZ. Derivative of that would give me a 4, there you go. Should be 0. Delta does not depend on Z, should be 0. Look at this being an easy exercise. I should have the formula written down, but I'm prone to making mistakes, so let's just go through the calculation and see what happens. It's correct, but maybe the best thing is just to peel out all the Z's, that would be nice. Minus AC 2Z plus 8 feel free to correct me. I think I'm still correct here. Yeah, I think that's it. So this is all the parts with the Z's. And then there's all the parts with the A's, or the constants. And if my mathematical skills do not trick me to write down something wrong, I think it's this. Minus 4 A. Am I correct? You might want to check this. Again, I'm doing it in real time, but I think this is good.
Also, a minus on the first term on the right hand side.
This one? Are you sure?
Because yeah, it goes minus minus and then moving it over to the other side.
Thank you. Yeah, you're right. It's this term. Two minuses gives us a plus, to the other side gives us a minus. That's right. There's that. You can divide the A out here. Okay, we have an expression for Z. Z then is AC there you go. There's that. Again, you might want to check the mathematics, but I think everything is correct. What it says here now is that if you know how many protons and neutrons there are in a certain isotope, you know the number A, you don't know how it's divided up into protons and neutrons, but you know it's a combined number, you plug that number into here, it will give you how you can make that combination of protons and neutrons most stable. How many of these particles have to be protons to get a stable nucleus, a relatively stable nucleus. That's what it says. Now I'm going to skip the algebra part. I'm just going to write down the expression that I got when you clean this up a little bit. So it's the same expression, just a little bit cleaned up. 1/3, 1/3, 1/3. It's interesting. In my expression, I have a big A to the power 2/3.
Because being divided, it goes on the top to being 2/3. No, I don't know.
That's probably the reason. Something like that going on.
What I just said is wrong, though.
If you multiply everything by A, then it's going to be 2/3 on top, right?
Yes. See if that solves all issues. You know what? Forget about my else. Might have made a mistake, but this goes to this real time now. Right? So, because of it, at some point, I'm going to plug in these numbers. You can see that the only parts that contribute are this one and this one, because the rest did not depend on Z. And that means that only these coefficients come into play, and if you look them up, the Coulomb term typically has a coefficient about 0.7. And this one has a coefficient of about 24. This is the semi-empirical part. You fit this to data, then these numbers come out. Now look at this expression now for a second. This is something that maybe we can throw away given these numbers. How about we throw away this part? A good approximation. This is correct, the full expression, but listen, what we have here is 4 times 24. Yes, it's about 100. What we have here is 0.7, and you have to divide it by a number 2. Now A goes in the hundreds for isotopes. So you have 0.7 divided by, okay,
yeah,
1/3 power or so of 100. Whatever you're going to plug into here is not going to make this number any bigger. So even without this part, it's already small, 0.7 compared to 100. let alone if you divide it by a to the power something anyway. So I'm, by a good approximation, this part I'm just going to throw away. If you do the actual numbers, I plugged in a very big number of A, 400. Okay, you don't have this in atomic physics, of nuclear physics, that you have nuclei with 400 protons and neutrons combined. And even then, this number was ridiculously small to that one, so you can very easily just throw it away. Let's see if we can clean this up a little bit then. And I think that we can. I have a 4A over here. Downstairs I'm going to put 2AC plus 8AA. There we have that one. Then with the big A's that we have to do something with. Put that one there. And if I'm not mistaken, that will give us A to the power 2/3 over there plus. I think that's it. Right, by very good approximation, the most stable Z's are these. This is ready enough to do the exercise, by the way, because the exercises ask you, well, to calculate the most stable isotopes. Now, we have a very good formula right now. Just plug in the number for big A, and you get back the Z that corresponds to a stable one. So there's that. So we can already do the exercise for this one. But I want to play around with this a little bit more. There's a 4, there's a 2, there's an 8. Let's divide a couple of things out. Gives us a 2 here, there's a 2, there's a 4. There's that. Here's something nice. And I love nuclear physics. Look at how beautiful this is. Here's something nice that's going to happen. Do you see that this number is probably also going to be small compared to that number? Again, AC is 0.7, this is 24. 4 times 24, 100-ish, right? 96. Now, of course, this AC, 0.7, multiplied by this A to some power, might at some point also become sizable if you make A big enough, this big A over here. So, I don't feel as confident as it was here to throw parts away with this coefficient. Because over here, what we had was AC divided by this one. So it was already small, it became even smaller if you put in big A's. So this I could throw away with certainty. Here, not so much. This is small, but this might become big. So I feel like I should keep it in there. But I am going to do the following. I'm going to take a 4AA out, gives me 1 plus AC AA, and there should be a 4 somewhere, I think. Where does the 4 go? It goes down here. There you go. This is exact, no approximation, just algebra. Here's a nice little trick. Ever seen this one before?
Yeah.
It's the first order Taylor approximation. Only holds that x is very small compared to 1. Now we have 1 here, 1 plus x, and I guarantee you this x is probably going to be small. Again, it's a small number divided by 100. Sure, it might become sizable if you make A big enough, but generally you expect this to be small compared to that. So, this, by good approximation, is 2AA so there's that. Note I've only made one approximation so far. I assume that this is going to be small, so I can throw this part away and I can make this step here. Alright, so far the mathematics. Let's look at physics. Well, one more step in physics. Some A's go away here. And there's a 1/2 in total. This is what you get. I love this part. The part where you're at the other side of the mathematics and start doing your physics. What happens if A is a small number? This A.
The Z goes to A over 2.
Exactly. If A is small, so if you have a nucleus that has only a small amount of protons and neutrons, you will find that this isn't very sizable, and then we're going to just throw this away anyway. And that means that at that moment, Z has become A over 2 for small a's. But you know that A is Z plus N. Yes? Tell me, what should Z be to make the most stable isotope? To the decay. That's exactly what we put in ourselves. This part here says, well, the semi-empirical mass formula tries to get N and Z is the same number. And apparently that's true, A is small. Yes, we get this out. That's nice. Now if A is big, not so small, we cannot throw this part out. We have to keep it. Tell me something. What does it say about the amount of protons versus neutrons? I don't need the formula, just the characteristic. If I cannot throw this part out, we know that for small a's, we find the protons and neutrons are about equal. If, however, you get a nucleus with enormous amounts of protons and neutrons in there, then this part is not measurable anymore. You have to take it into account. And you also can draw a conclusion about the number of protons versus neutrons. You might want to play around this a bit. This is a mathematical exercise.
The protons should be less than the neutrons.
This is what you find if you do the mathematics. You can already see it here, yes? The amount of protons is about half the amount of protons and neutrons together, but a little less. This thing takes away from the amount of protons. Now, if throwing this away already gives you Z equals M, then making Z smaller will give you that Z is smaller than M. And that's exactly the answer to your question. That if you have high isotopes, as in nuclei with enormous amounts of protons and neutrons, then you will find that it actually becomes more stable if you put more neutrons in there. Your lead is an example.
Yeah. No, I don't follow that logic.
No?
No, because then you get to uranium and all the lactinide series, and that logic falls apart as well.
I don't understand. One more time?
So then, but then you get to all the lactinide series, uranium and curium and
yes.
plutonium, and that logic would fall apart again.
Wait. The statement is not that these ones are stable. The statement is that they're as stable as they get in that area. So that means that they will fall apart, you're exactly right, it's still radioactive, but doesn't fall apart as quickly as the other ones.
Okay. Yeah.
That's a different
thing.
Okay.
I mean, it's right, I mean, the math makes it work out.
Yeah, but isn't if the protons were more than the neutrons, then you start having more proper decay, I don't know.
There would be more unstable, right?
Yeah.
Right.
For sure.
So, just to get all the misunderstandings out of the way, the statement here isn't, or this statement that we started out with, the statement isn't that that thing itself is going to be stable. It just says that of all the particles, all the nuclei with that amount of proton, with that A number, these Z numbers are the most stable.
Mm-hmm.
That's a different statement.
That's true.
And this, I think, is why when you look at tables of isotopes, you will find that the higher ones have more neutrons than protons.
Yeah.
There's another statement I would like to make. And I forgot what it was. So apparently it wasn't very important. It'll come back in a second. How are we on time?
It's 12.
Okay, well that's perfect. Well, it is actually. Look at that. There's.
It's 12.
Of course it is. 3 times. Confirmed.
All right. In a second, when we get back, I'm going to use this one and actually do some examples. It's a very handy. I love this one. This is, by the way, exactly the expression that I had here. So I never made a mistake. I'm so happy. Okay. Look. Yeah. Okay. Makes me happy.
I understand the confusion now. So my initial question was that we were considering the case where the one of the terms that makes the number of protons be equal to the number of neutrons. We were talking about that, or
Yes.
the difference be close together.
Yes.
And then the lead example searched to show that that difference is very big.
Yes.
Yet it's stable.
Yes.
But this proves that the number of protons must be less than the number of neutrons. Not that that discrepancy can be so big, yet it can be stable. So for lead, it would be 210 minus 82 or something.
Yeah.
Like 130.
Yeah.
That's a huge number.
Yes.
And that's my confusion, because I mean this shows that the number of protons should be less than the number of neutrons for it to be stable, and I think that's completely right.
Yeah.
But the fact that that difference is so great in lead, yet it's one of the most stable isotopes, is still the confusion. I don't know.
No, but we cannot, for any specific example, I cannot get this out of here. Yes? Well, in the exercise I'm going to see in a second, we're going to see more exceptions to the semi-empirical mass formula. You see? Yeah?
No, go ahead.
Okay, the only thing that I can say now is that this is a general thing. It doesn't say which ones of them are actually stable. It just says it's the most stable one given a number A. That's all that it says.
Yeah.
Secondly, what the semi-empirical mass formula does not take into account is magic numbers.
Oh.
What we have in the nuclear shell model is that there are exceptions to stability, namely if the number of protons and neutrons happen to be one of this sequence, then it becomes exceptionally stable. We never put that in. Now what the example we're going to do in a second is that we're going to calculate what this number should be according to the semi-empirical mass formula, find that it's not the number you actually measure, and then we remember, oh wait a minute, but this one is magic. So that's a drawback of semi-empirical mass formula. It doesn't take the nuclear shell model into account. Coffee and an apple. Well, that's my plan. Okay, thank you, yeah. Alright, how are the energy levels?
Described.
Oh god.
That was worse than mine. That was worse than my con, right?
Yeah, that was
Thank you.
I knew it was only going to be a matter of time before somebody turned this into a quantum mechanical joke. Yes. Okay, let's discretize energy, sure.
Mine was worse than mine.
I'm disappointed in both.
Some exercises I would like to do with you using this beautiful result right here and the full semi-empirical mass formula. The first exercise about the semi-empirical mass formula, you might recall, had to do with the question, determine which isotopes are the most stable. And already almost there, because what we've already determined is, erase this for a second, what we already determined here is, given a fixed number A, then which of all the isotopes with that number A is likely to be the most stable. That's this expression right here. Again, we threw away something, one part, but as I showed you, that part really is manageable, even for big A's. And you can play around with that a little bit. That part that I threw away here at some point, at one point doesn't really become relevant. And I found that it only becomes sizable compared to what I threw away if A was in the 400s or so. And as far as I know, we don't have isotopes like that. So it really is a good approximation. So this is what we already have. That given a fixed number A, which corresponding Z is then the most stable? Here's a nice question. How do you get the A's that are the most stable? We now have given a fixed number A, which number Z you have to put in? How do we get the most stable A's? There's at least two ways that you can do this.
Can't we do it the same way? Differentiate with going to A.
Okay, what do you keep constant in that case? You keep. Oh, that's one way of doing it. That you would say, you know what? Just as we differentiate this with respect to z to get the most stable z's given an a, you could also do the opposite calculation. Keep z fixed. And then do this. Do you agree with me, by the way, that this is really just the same thing as doing this? I mean, if you're going to shift A around a little bit, but Z is fixed, and you're really just shifting N around, yes? So it's really just the same thing. You could also do that. But yes, this is one way of doing it. And then you get a similar expression like this. In fact, I see a nice midterm exercise coming up here. Well, you already know what I'm going to ask now, so this is good news. And you get the isotopes with how many neutrons you have to put in there to make it the most stable. So that's nice. Here's another trick. This expression gives you the most stable z's given a fixed number of A. What now if you plug this into there, all z replaced by this expression? What you will end up with is an expression for the binding energy that now only depends on A, because all the z's get replaced with something with a's in there. So this one was a function of C and A, and by plugging this into that you get an expression that only depends on A. It's not the same expression, because this one allows for all kinds of isotopes, including the ones that are not very stable, and this one only allows for the stable ones with respect to Z. Alright, now differentiate this with respect to A. It's now a full function of A. You will get out, and you set it equal to 0, you get out the most stable isotopes for a given A. Let me rephrase that. What you get back is for what A value an isotope is most stable. But what we already plugged in was that it was already most stable for Z. So what you can do here is find an expression for A for which nucleus is most stable. This one. Given that Z was already the most stable ones. Now it's a nice exercise to work out what the expression is. It's just an exercise in taking derivatives. And then we're all done, yes? Because we've already optimized Z to get the most stable ones. We got here, we took the derivative with respect to A, so now also stabilizing for the amount of protons and neutrons together, and then we're all set. Because this final expression that you will get will give you everything that you need. You take a number A, one of these numbers that comes out. You say, okay, well apparently this is the A for which it is most stable. Which Z's correspond? Well, you take that A that comes out of that, plug it back into here. And you get the Z's that are the most stable. You get the most stable one. If you do the exercise, I think nickel will come out, or one of the irons. One of the ones that, if you calculate this, right, do something like this, you get this one or that one. So that really works. That's nice. Again, it's an exercise in algebra, it's not very interesting. But this is how you do it, this is the math.
No, sorry. So, just to repeat. I would plug in the Z into that, that's fine for A.
Yes.
I find the specific A, I plug in the A, and then after I plug in the same value, the initial value of Z in, according to the A.
Yes.
Okay.
So you get the Z's.
Yeah.
So, yeah.
And plug them both in the top. Yeah.
Yes.
Okay.
And there you are. And then you have the number of Z's, you have the number of N's, and you have the most stable isotopes. And they will correspond to the local maxima there. So there's that. That's nice. Let's make it more specific. It's an exercise that we already did a little bit of before, which just going to do it again. You might remember from, I think it was last week, that we took a number of these isotopes and just checked if they were stable or not. And we now know exactly how to do that. Here's the example. Suppose that you have this exercise C, by the way. That A is 191 protons and neutrons put together, so that's a fixed number. And the question is, okay, well, given that you have to make a nucleus of 191 nucleons, how many of them would you want to be protons in order to get the most stable one? And the exercise should be simple now. You just put it into here, yes? By the way, this number, this is a fixed number for all cases. I calculated it, it's about 7.4 to 10 minus 3. So you can very easily just plug in 191 now, calculate what Z should be. You will find that the element, the amount of protons that is the most stable is this one. Where is it? 72. This is what you get out. Why? Just do math. Plug in the numbers. 72 is hafnium. What I do then is always look on Wikipedia what the isotopes are of hafnium, read a little bit of hafnium. It says, Wikipedia, it's a luscious silvery metal. And I never expected the word luscious to be on the Wikipedia page on chemistry, but it was there. A luscious silvery metal.
What does that mean?
A luscious.
Scientifically, like, what is that?
I have no idea. I mean, I know what it means.
On a scale of what? Like,
well, compared to,
luscious.
I don't know, compared to plain old iron or something like that, or I have no idea. I mean, I know what luscious means when you talk about food or people or something like that, but chemical elements, not so much.
Chemist.
Don't they say coarse, smooth?
What?
Don't they say coarse surface, smooth surface?
I think it means, but
that makes sense.
I think that's more objective. Yeah.
Maybe that's what they meant. I've never seen a piece of hafnium in my life, so I have no idea what it actually looks like. But apparently it's luscious, yes. So I feel a good opportunity for me to learn what the word luscious means. Actually, just have to find myself a piece of hafnium and I can extend my vocabulary there. Okay, so this is what comes out. Now here's something interesting. This piece of hafnium, so that will be 19172 HF, has a half-life that I just looked up of, oh, actually, there's no isotope. Yeah, I don't know how to write that down. I mean, there's no isotope with 191 of them in there.
So it doesn't occur naturally?
No, and also not synthetically. It doesn't occur.
Yeah, so
it just falls apart, apparently.
Okay.
So, think about it for a second. Let's ask you a question about that in a moment. If that is an issue, if we made some terrible mistake somewhere. Here's another example. A is 111. You can play this game with all numbers, of course, yes. 111, we put in Z. In our calculation, the most stable one that will give you is, by 111, is 66. So you go to Wikipedia, you read all kinds of adjectives about this particular material, and it appears it's rhodium. RH. 111, 66. Half-life, looked up. Half-life was 11 seconds. Here's a question. In that same table, there's a Wikipedia page on the isotopes of rhodium. You can also find other isotopes of rhodium. 66 is the same, this number is different. Other isotopes with different half-lives. Of course, with different half-lives, but with longer half-lives. There is one that takes a couple of hours to decay. More than 11 seconds. There's also one, I think, 6 days or so. Well, that's strange. I mean, didn't we just calculate what the most stable one should be? And apparently what we get is certainly not the most stable one, because there's one that takes 6 days. Am I making a mistake, or is the math making a mistake?
Is there magic somewhere?
No, but this is not a magic number, no. Yes.
Neither of it should be a mistake, because we made approximations, and so we get to a ballpark figure. But so, for example, you probably, when you solved that, you probably didn't get 66. You probably got 66.5
Yes, but you don't get exact numbers out. No, that's true.
Yeah.
Yes.
And so the approximations would mean maybe the stable isotope is 67, in which case you're off by a very small percentage, which is fine.
I found 46.
46?
And then I tried it with the one without approximating stuff, and it's 47.
For which one?
Instead of 66.
Oh, I'm so sorry. No, the rhodium. No, you're right. No, the rhodium has 66 neutrons in there. No, actually, you're very right. Yes, I'm sorry. Z is not 44. Okay. And so the difference between 66 and 111. Excuse me, that's my mistake here. I have it right. I mean, my notes are correct. It's just my translation on the board wasn't correct. So what was the number? Did you say?
I got 46.
46. Okay, 46. Apparently I abbreviated to some other number or so because to get 111, but it's something like this, yes? 46. Oh yeah, I got 45. So I probably made some, so it's 45 to make it rhodium.
Okay.
Let's just stick to this example for now. Back to my question. This is still correct, by the way. I just translated wrong from my notes. Back to my question. This is not the most stable isotope of rhodium.
Yeah.
And you're saying now, well, maybe in our approximations to get to this formula, maybe an approximation or two approximations, maybe those approximations break down, and if you would actually do that, this number would be a little bit different.
And that's all we want. Maybe the stable one is 46.
Okay. That's a nice question. Might be right. But there's a bigger mistake. It has nothing to do with approximations or the math or the semi-empirical mass formula. It has to do with me not understanding mathematics, understanding interpretation of mathematics. I was never expected to get the most stable isotope of a given element out.
One of them.
What I was looking for is, given that you have all kinds of elements, the isotopes of those elements that have 111 protons and neutrons in there, which one of those is the most stable one? I never said I'm going to look into the whole rhodium catalog to see which one is the most stable. That's not what I did. I looked at all the isotopes that have 111 particles in there, including rhodium and the ones around it. And of those, rhodium is the most stable one. If you look that up, that is actually true. So it's just my interpretation of the mathematics that was, or my interpretation of the physics that was wrong.
Yeah.
To say exactly the same thing in somewhat different terms, I maximize with respect to Z. So I'm going to get the Z out, the element out that has the most stable isotope 111. I kept 111 fixed and I played around with Z. I did not keep Z fixed, so I played around within rhodium. That's what I did. So that this is not the most stable isotope of rhodium is not strange. Same answer here. Alright, two nice examples. Let's look at xenon. This is an example that we did before, but it's good to do this one more time. Suppose that we have xenon, and xenon has, I never know these things by heart, it's 55 protons, and it has 142 xenon. 142 mass number. Yes?
So I have a question about before. So why would a different isotope for rhodium, sorry, that's how you said it, be better? Because does it then just depend on the electron configuration that affects the stability?
No, the electrons have nothing to do with the stability of the nucleus. Well, sometimes the nucleus grabs all of the electrons and it makes it a little bit unstable, but if we never put it in there, not in our nucleus shell model or not in our semi-empirical mass formula, so that could never be the reason. And the question is?
So then what about rhodium makes that other number, or Newton A or Z number better than the one that you predicted for all chemicals with that kind of, I'm explaining this.
No, I'm not sure you understand the question. I mean, I'm sure that's a good question, it's just I don't understand the words.
What is the property of rhodium that means that the most stable configuration does not match up with the one that we predicted?
Why are other isotopes of rhodium more stable?
Yeah,
Okay.
basically, why?
Why this is not the most stable one of rhodium?
Yeah.
Okay. That was the trick question that I asked just a second ago, yes, or a minute ago. Then why, of all the isotopes of rhodium, this one is not the most stable, even though this will come out of a calculation? I think this is your question?
Anyway, yeah.
Okay. Can somebody answer?
So that's what you said, where like we weren't calculating the most stable rhodium isotope, we were calculating the most stable sort of
Mass.
Yeah,
Total
exactly.
mass. The
That has
neutrons
111.
plus protons, which is the 111.
yeah.
So there might be a different configuration where the sum of protons and neutrons is always 111, but as soon as it's a different proton, it's not anymore that element, it's another element.
Yeah.
So we only check a couple of the, maybe this one, and all of the other ones fall in another way.
Yeah.
Like, sorry, I feel like there could be like other rhodiums that have different, like instead of 111 they have some other number, but also 45 I think. So it's still rhodium, but it's a different,
Different mass.
yeah, it's a different A than what we checked for. So it might be more stable.
Oh, okay.
Maybe maybe it's a little bit of overkill, but it's an important point. Suppose that I find, here's rhodium, 45, that is 111, yes? And here's another some other nucleus. I don't know these things by heart, so I'm just going to make up a couple of them, okay? Alright. Might try to think about why I put those numbers there, yeah? Suppose that this has 50 pro. I have no idea what that is, but 50, yes? This isotope might exist as well. And here's another one. 37. ST. Picking up why I choose these combinations?
That's different people.
Yes, thank you. Here. Let me put another one in there. Here, you see that's me. There you go. Okay, there you go. I have now a bunch of isotopes that all share one thing. They're 111 total mass. What my formula here does is select out which one of these with 111 is the most stable. What it does not do is look at all the other isotopes of rhodium where this number is fixed and all the other ones. This might also be isotopes of rhodium, yes? Same Z, different A. What this formula does is, given that this number is fixed, which one of these is the most stable? What it does not do is say, well, of all the rhodiums, which one is the most stable? This is what it does. So I'm not surprised that I find that this number is the most stable of these, but it's not necessarily the most stable of these. That's the difference. All right, back to xenon. 142.55. We can use our little cool formula again, because the A of this thing is 142. And we can check whether this thing is, how stable that is. A is 142. If you plug it into our neat little formula, again, it will go through all the isotopes that has 142 total mass, even though it's going to be different elements. And it's going to look for that element with mass number 142 that is the most stable. And you will find, if you plug that in, I found 57. That the Z that is the most stable is 57. And I have to look it up again. Oh, I did not look it up. Does anyone know by heart what 57 chemical element is? I have no idea.
Well, lead is 56. Sorry? I think lead is 56.
Okay, so it's one above lead.
Lead plus
No
one.
idea which one that is.
Or sorry, not lead, I meant iron. Lead is like 82, sorry.
I just have no idea.
Lead is
Which is
Barium.
which
No,
one?
it's not. That's 56.
barium is 56.
Yeah.
Atomic mass. Proton number.
Yes.
Barium. No. Yes,
Is that-
barium.
So which one?
Barium.
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 It is
That's
BA.
right.
Where?
Say?
56.
What are the letters?
57.
Oh, 57.
That's what I meant.
Oh,
I was
that's
telling you
not-
that it's not that. It's, yeah, exactly. Lanthanum?
Lanthanum.
Is it LA?
Okay.
Yeah.
Last one.
Lanthanum.
Yeah.
It's probably some luscious metal or something.
It's like the extra part of the
Yeah,
periodic
it's
table.
just
It's
where
not,
like-
yeah, it's that.
Okay.
Yeah.
Alright, so apparently that's this. So if you were to have an isotope with 142 mass number, and you have to look through all the isotopes of 142, it will select out apparently 57 protons, this is lanthanum or whatever it is. Now xenon is not platinum. Not the same. So what does nature try to do? It tries to get to the most stable configuration. So we'll try to get from here to there. Now sending out an alpha particle will not help it. Because the alpha particle brings down this number. And you want to stick in 142. Fortunately, a gamma radiation also doesn't help because gamma radiation doesn't change any of these numbers, it just changes the energy. But beta plus and minus, that does help. It changes a boy into a girl into a boy, but the number of people stays the same. 142 stays the same. So there's a neat opportunity for nature to keep the 142, but up the number of protons. And the question then is, which of the radiation types would it utilize to make that happen? And this is just you having memorized how beta radiation works. There's two types, plus and minus. It will be minus because it takes one of the neutrons and turns it into a proton. This number doesn't change, this number goes up 1. So a neutron is sacrificed to get another proton, and energy conservation charge conservation then tells you it has to send out an electron. Oh, plus a neutron, don't forget about that one. There you go. So apparently, if you start out with this one, and nature wants to be here, it does so by sending out beta minus radiation. That's very nice. That means that if I now give you a certain isotope, you can now predict what kind of radiation it will send out. Just based on our little exercise here. And if you want to know how often it does so, you do the calculation. That is one of the homework exercises with the Fermi-Golden rule. So how beautiful is this? We now know how thingies decay, and you can calculate how often that happens. Yes?
I'm sorry, this lead example is still bothering me. So I looked up the number. I'm sorry I keep bringing this up. And so lead is, the most stable isotope of lead is 82 and 204. And that doesn't decay at all. It's completely stable. And when you plug in 204, which is the mass number, then you get, for Z, you get 76.
Yes.
Which is not 82.
That is correct. Yes.
So, but it's not going to decay to anything, lead 82. And this doesn't.
Yeah, no, I understand. Well, the question still stands, and I don't know the answer. There's apparently something else preventing this from happening.
Yeah, and I mean, just my only problem with this is that I mean, it's beautiful that it works and everything, but it doesn't work for everything.
No, I know, but this is not unexpected. This is the comment that I gave you last time as well. This is really just an attempt to get all the terms right. There are many isotopes who do not follow this trend. Generally they do. Of all the 200-300 isotopes, they follow this trend with only small differences in the order of 10%, but there are ones that are really different. And one of the reasons for that I already gave you, it has to do with the nuclear shell model, say. But there might be other factors contributing as well. If you really want to do this, you have to do the full quantum chromodynamical calculation that nobody is able to do. So it might be that I don't know the answer, but you know the next guy does. It might also be that it's just not been completely figured out yet. I mean, I certainly don't want to give all of you the impression that all these models work. Nuclear physics is one of the parts of physics that is, well, I wouldn't say the least understood, but doesn't have one underlying model that works for all cases. Right? I mean, look at this alpha radiation. We had to do some little trickoids with classical physics and quantum mechanics. Beta radiation, Fermi-Golden rule. Gamma radiation, we would have to use quantum field theory. So there's all kinds of different tools for different jobs, and none of them completely overlap. It might be, by the way, that the lead example has been fully worked out, and it's just me that doesn't know the answer. But generally speaking, there are many exceptions to the rules. Unfortunately, I would have to say. It would be nice if there's one model that works for all. It is something we have to look into, because I'm now very interested to what makes lead this one fine example.
I mean, even with this, for example, I mean, how can you be sure that xenon actually decays? How do you know that xenon is not just one of those contrary isotopes?
We don't.
Okay.
I mean, it sort of gives us an idea, and in most cases it works. And I can assure you it's in the ballpark of 80–90% it works. But there are exceptions, yes. No, it really does.
Okay.
But you're right. I mean, it could well be that this is one of these crappy examples like lead is. That we make this prediction and it doesn't work at all. Just in your example with lead. We don't know.
Okay.
Alright, so that's nice. One of the other exercises, what is the binding energy of an alpha particle? You take an alpha particle, you peel it apart. How much energy will that take you? Will it cost you? Now, you know, of course, an alpha particle is this helium nucleus. And, well, one thing I can already tell you, this is probably not going to be a good approximation. Excuse me, this should be a very good approximation.
Yeah,
because A is a small number. Yes, 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 yes. But we're not going to need it anyway. So the only thing that we need is the binding energy. The binding energy is by definition the energy that it takes you to peel apart these things. Or it's the energy with which they're holding on to each other. So that's the energy you have to put in minimally to get them flying apart from each other. So how do you do this? Well, you first recognize that helium has the Z equals 4 protons. That's exactly wrong. It's 2 protons, 2 neutrons. There you go, trying to do the math there. I mean, it's something wrong. You should know this by heart. 2, 2. And you just plug it into the Semi-Empirical Mass Formula. It gives you a number. The number that you will get out is that the binding energy is, I believe it is 21 mega electron volts.
Yeah. Yes, that's right.
Yeah, that's right. Yeah.
It's like
Okay.
21.9.
20.9, so 22-ish.
Yeah.
Okay.
That's right.
Now, what people typically do when they look at binding energies is they look at the binding energy per nucleon. I hope you see why this is a good reason. That people rarely, if ever, look at just the binding energy. They always look at binding energy divided by the number of protons and neutrons. So it's this number that they actually look at. Why does it make sense? Why is that a more important number?
Because we don't differentiate anymore between the particles that are at the surface or at the center. We kind of have more an average. Because it's not like the last time you just broke it up, like in the middle it's all like alpha particles.
Yes. Oh, I see what you mean. Yeah, okay, so you get much more of an average because the nucleons at the sides have smaller binding energy than nucleons in the middle, something like that. Oh yeah, that's actually a good example. Yeah, I never thought of that. That's pretty good, yeah. Gives you an average binding energy. So you don't have to differentiate between the ones at the surface and the ones in the middle. No, that's cool. There's another reason though. If you want to compare, say, how stable helium is to some isotope of uranium or so, well, helium is going to be, well, let's take 2 stable ones. There's a stable one at the low A's and a stable one at the high A's. Now, I can already tell you that the stable one at the high A's will have a small, will have a big binding energy because you have lots of particles. Yet it is easier to pull apart. I mean, does it make sense physically for you? If you have lots of protons, neutrons together, some nuclear force doesn't pull as much.
Yeah.
So it's going to be easy to peel that one apart, even though it's stable. Whereas if you would calculate the number, the binding energy would be a bigger number for those high A nuclei. Right? You just have more particles, so there's more binding energy. So just calculating binding energy will give you wrong predictions here and there. One other way of saying exactly the same thing is saying if you want to peel apart a nucleus, what you do is peel apart nucleon by nucleon. And if you want to know if that's easy or not, you have to calculate how easy it is per nucleon to pull them away from each other. So this is the most interesting number to look at. In our case, 21 mega electron volts, this is what Semi-Empirical Mass Formula tells you, divided by 4 will give you a 5 point something or so. I can do better, that's 5.5 I guess, right? Something like that. Yet if you do the measurement, so this is theoretical, based on the Semi-Empirical Mass Formula, if you measure it, you will find that this number is around 7-ish. Apparently it's more difficult to peel apart an alpha particle than our formula predicts. Why the discrepancy? It's a big discrepancy, it's about 50% or so. So why?
Magic numbers.
Magic numbers, exactly.
Magic, yeah.
It's because of matching numbers. This thing doesn't take into account that there are these preferred numbers of protons and neutrons that make it more stable. That's never built into there, so it also doesn't come out. Is your lead example, is that magic?
I just realized 82 is a magic number, that's why I was going.
There we go.
I was waiting for the right opportunity.
Okay. Okay, there we are. There we are. Okay, so lead apparently is single magic, right?
Single magic.
Single magic, okay.
Very close to double magic, actually.
What do you mean very close?
By 2. The next one is 126 and this is 122.
And does 126 exist? Oh, in magic numbers. The next magic number is 126. Okay. Alright. Oh, okay. It feels like part of the mystery has been solved by now. Oh, wow. Okay. Learning something here.
Yeah.
Okay, so yes, the discrepancy, of course, is magic numbers. Okay, so there's that. Now, one final one, and then I would like to say something about the midterm from next week. One exercise is the following. That if you have uranium, 235, uranium 92, you can fall apart into these parts, 87, 35, Br plus our good friend La that we saw before, and 3 neutrons. Apparently this is a decay that can happen. Okay. The question is, how much energy will that liberate? I mean, it falls apart, so apparently it will release energy. The question is, how much is that number? The number itself is not so important. The question is, how would you calculate it?
The difference.
So the binding energies?
That's exactly right. I mean, this is a binding energy. Yes, tries to keep this is binding energy. This is a binding energy. The binding energy of this thing in itself is not released because this thing still sticks together. Yeah. Same thing with this one. But this one has lost so much of the binding energy. The binding energy that tried to keep these two together. Not within this one, not within this one, but how these two were together. So what you do is you just calculate the binding energy for uranium. This one of this element Br. And I think this is a lanthanum.
Only that.
So you have 3 binding energies, and you know how to calculate these, of course, because you know exactly how many protons and neutrons are in there. So just plug in the numbers. And this one is uranium. There you go. And then there's a difference. These 2 binding energies give you a number. This binding energy gives you a number. The difference between them is apparently how strongly uranium tries to keep these 2 together. I'm not taking into account this one. Why?
They're not bound together.
They're not bound together. Now, typically, one nucleon, if you look at the Semi-Empirical Mass Formula, this one, it trails off here-ish, yes? Meanders around this point. That's about 7 MeV per nucleon. That's the number that sort of floats around. If you're here-ish, with big numbers of A. So in other words, each of these single neutrons, will have come apart by using 7 MeV or so. So if you want, you can put in 3 times 7 MeVs, something like that.
Mm-hmm.
Now, subtract all of this from all of that, you will get a number out. I did that, was about 150 or so, comma something something. Now, of course, the physical reasoning is much more important than the actual number, but what I found was that the energy that is liberated is just the difference in binding energy, and that was about 150, something in MeVs. So there's that. Is that a big number, by the way?
I think so, because uranium we use it often for. We should have one of the biggest.
Okay, that's an answer. That's an answer out of context.
Yeah,
out of, an answer from within physics, maybe. So what's the typical scale? Do you know? Just by reading Martin, maybe.
Using the alpha particle. As a.
Well, as a reference guide,
yeah.
This is about 7 MeV per nucleon, right?
Yeah.
100 MeV, yeah, that's pretty sizable.
Yeah.
In nuclear physics, the the order of magnitude to look for is MeVs, tens of MeVs. That's the order of magnitude. Atomic physics, EVs, and within the nucleus, you're looking at GeVs, something like that. Okay, now we have about 7 minutes left, unless there are any questions. Nope. But yes, please, go ahead.
So if you're trying to find the most stable configuration of a single element, you could just use this formula as well, right?
Yes. Yes. But with some caveats that are counterexamples. For instance, because of magic numbers and such. So it's certainly not this example that we just had before with the xenon. It's a good question. I mean, how do you know that the number that comes out for xenon is actually the right number? It's not just one of these crappy counterexamples. You don't. It works in many cases, and there are individual cases where it doesn't. It's just our lack of understanding of nuclear physics. Strange, right? I mean, we understand the theory of quarks better than we understand nuclear physics, even though nuclear physics is just made out of quarks. But then again, that's no different than biology, where one single cell is much more easy to analyze than a complete person. You put more of them in, it becomes more difficult. Same thing here. So this is why we only have these sort of approximate methods, and these different methods for different problems. And all of them have somewhat overlap, but not all of them work for all cases. That's really because of that reason. Particle physics in that sense is easier. Yes?
Can I ask a small question? So that 7 that you substituted for neutron, what energy, is that the neutron rest mass? Or is it the energy of the,
no.
Energy of
No. It's the binding energy per nucleon that you would typically have in a big nucleus. Because big nuclei have as energy per nucleon around 7-ish. So this neutron was originally in the uranium, so it has to be peeled apart at some point, and apparently that costs around 7-ish. That's where I got it from. Now, if you calculate the rest mass of a neutron, it's much larger number. The neutron is about 1 GeV in energy units.
The rest mass?
Yes.
Oh, electrons like 500.
500. I think it's MeV, yes. 500
K.
Sure. Can you look it up just to be sure? Do you have?
I did gamma ray spectroscopy for it.
Then you probably know the numbers better than me. So
it gives you the characteristic peak, the annihilation peak at 511 K.
Okay. KeV. Well, if you'd be so nice to look it up, then in the last couple of minutes, let me say something about the midterm of next week. These exercises, by the way, I'm going to put on Eleium, so the full word solutions. It's either going to be today or during the weekend. The same thing, by the way, with the exercise I'm going to discuss on Tuesday, because you will need a couple of days, I guess, to go over them. They won't be as quickly as these ones, because I just have to type them in. Takes me a while, but I expect Monday-ish, maybe Tuesday-ish, something like that. Okay, so midterm. So what to expect? Well, one question that we got from individual people was, do we have to do all the derivations? And the answer is no. I won't ask you for the full derivation of the Fermi-Golden rule or so. The only reason that I showed you is that I don't want to give you just a formula and tell you, well, apparently somebody figured out that this is true. I want to show you, the theoretical physicists that you start out with a number of small number of postulates, you get big results out. So what will I ask you to do? Well, these kinds of exercises that we did just now. So that's one. I'm going to make a little listing. I am going to, that's not Q's red, it's such an ominous color, just green. Okay, so the, well, let's call it quantitative examples, exercises from the tutorials. So the ones that actually ask for numbers, quantitative exercises. What's the type that we just did? Calculate what this number typically would be, something like that. I'm going to ask you about the SEMF, and the SEMF is simple enough, the Semi-Empirical Mass Formula, that I can actually ask you to do the derivation of that. right? Take a derivative, show that this happens, such and such.
Harmonic and
Sorry?
is the spherical harmonic or
No. That was nuclear shell model.
the shell model?
No, that is. I think that is a little bit too big to.
Okay.
Yes.
Yeah.
So I do the Semi-Empirical Mass Formula, and this is easy enough mathematically that I can actually just ask you take derivatives, show the formula will typically be for this and this, most stable, etc., etc. So this is more derivations. You should be able to do those. Not that difficult. One very important thing about the nuclear shell model, is that if I give you how the shells work and what their respective energies are, then I can ask you some quantitative questions about that too. That if I give you this listing of where the levels are and what the energy differences are, that I could tell you, well, if you have this nucleus and you would fill up using nuclear shell model, what would typically be the binding energy? Okay. So, how to put this nuclear shell model? Application. Maybe that's the best way of putting it. I'm not going to ask you for a derivation, but I'm going to ask you to apply it. Now, about 30–40% of the midterm is going to be about no calculations, just what is the physics behind this and this result. So let's call them essays.
30% of the minute.
Something like that.
Yeah.
Yes.
Okay. Mm-hmm.
Grade-wise, I mean, I have no idea how much time it will typically take you or the next person, but essays, as in, well, you have this formula. What did we put in there to make sure that this works? Or I would have you calculate one of these things and say, well, it doesn't agree with experiments. Can you explain, knowing what we put in there, why it doesn't agree anymore?
Magic.
That's not always going to be the answer. Trust me, that's not going to be the answer to every question.
Triploids and magic.
That's a good.
I once had this student who understood for me that if you have the Dirac equation, you can pretty much, well, almost up to everything, calculate everything in for fermions. So he went to his chemistry teacher, chemistry exam, and he actually wrote that down. I said, well, apparently everything about electrons, which is a fermion, is in there. He hoped that he would get a good grade. He said, well, this already encapsulates everything, right? And then, of course, his chemistry teacher did not give him a good grade. It's like going to your mechanics course and write on this. There you go. No, now. It's not that easy. You have to be able to find them out. Okay, so there's these essays, and I'm going to ask you some quantum mechanics. Now, by quantum mechanics, I am going to ask you, well, derivations is too big of a word. It's not going to be the kind that takes you 500 years to write them down, but I am going to ask you, say, you have this commutator. Yeah. Calculate that it's actually true, that it works like that. And what does it mean physically? Yeah. So let's call it basic quantum mechanics plus meaning.
But no mathematical manipulation involving QM.
Well, I can envision an exercise where, say, you have to show the equation with this thing, and I make it easy enough, or I just put in a sequence of steps that you can go through. But no spherical harmonics, say that this is too ridiculously difficult. But for instance, this exercise that is now part of the homework for Tuesday is about the tunnel effect, and it's split up in easy pieces.
The one in the email, or
the one that I put on a yesterday. That would be an exercise that I would think, well, that you should be able to do. Especially because I say, well, this is one result, show that's true, using that result, show that this is true, etc. You should be able to go through that. That's about it.
Will you be uploading a chart?
It's next week.
Yeah, I could, I think.
You don't have anything like that.
Predecessor has a couple of these exams, but she focused on more topics, less time per topic. So it might be that if you look at those, you might find that there's some topics that I haven't covered. So it's not very representative. What I could do though is look at these at her midterm and select the ones that I would also typically ask. And you forget about the other ones. I think I will do that. I have one more, everybody. On Tuesday, you're going to show us how the alpha calculation works. the tutorial I will also go through the full beta calculation as part of homework to see if you got through that. There's one final thing I would like to discuss theoretical wise on Tuesday, and that's selection rules. What we now have is that we know from quantum mechanics how you can calculate the rates, what kind of radiation there is and why, and how a typical nucleus will decay to some other nucleus, why it would prefer that particular direction of decay. What I have not told you yet is that there are also some decays that might be possible from an energetic point of view, according to Semi-Empirical Mass Formula, but still don't occur because of conservation rules. Now, that is not quantitative, it's just knowing the rules and knowing how to apply them. There are in Martin. Unfortunately, I don't know the sections by heart, but I will put it on the layers. And we'll send you an email say, well, if you want to be prepared for the lecture, read this and this and this part. For instance, gamma radiation. Did you know that gamma radiation takes away a little bit of angular momentum? Photons have spin, yes?
Yeah.
Photons are spin 1 particles, so they have angular momentum. But you also have conservation of angular momentum. So if you start out with a nucleus that has a certain angular momentum, and you want, as far as energy is concerned, it wants to decay into this other nucleus, then you have to check whether beginning and end nucleus have a different angular momentum that agrees with the photon that sends out. Otherwise, it's still not allowed. So there are selection rules, as they are called. Let me just send you an email where you can find them in the book. I'm going to discuss them on Tuesday, and that's the last part. Then the whole nuclear part of the course is all done. You should be all ready. Yeah?